Welcome, and thank you for joining us for this webinar presentation. We are the Defense Systems Information Analysis Center, or DSIAC, one of 3 IAC domains in the DoD Information Analysis Centers operating under the Defense Technical Information Center, DTIC, within the Office of the Undersecretary of Defense for Research and Engineering. Our informative webinar series highlights current and emerging research and technology developments. It presents an opportunity for accelerating the DoD's leverage of these advancements by increasing awareness and fostering technical collaboration. DSIAC serves as one of the premier information research partners and curators of technology advancements and trends for the defense systems community. As such, our organization supports those working in the defense systems domain of DoD research and engineering. We do so by helping navigate the vast landscape of scientific and technical information, allowing our customers to get a head start on their technical projects. With an understanding of the defense system's DoD research and engineering landscape, we provide research and analysis services. We help unlock access to information, knowledge, and best practices from government, industry, and academia to stimulate innovation, foster collaboration, and eliminate redundancy. We hope you enjoy this webinar presentation and that it serves as a catalyst for community collaboration and improved DoD defense systems research.
All right. Well, good morning, good afternoon, good evening to everybody who has joined us. Thank you for joining so far. My name is Brian Benish with DSIAC, the Defense Systems Information Analysis Center. Hopefully you're able to see and hear our little commercial there to kick things off. I'm pleased to have Doyle Moats with us. Doyle's going to be bringing up the slides that he'll be walking through and for the presentation that you're all here for. But before we begin, and as he's doing that, just a couple words about the logistics of the webinar, kind of schedule and how we're going to run things. First thing I want to do is point you to the web page for this webinar on DSIAC.org. If you go to the web page related to this webinar, there should now be a button to download slides and be able to follow along. If you do get disconnected for any reason, you can grab those slides. But also, we are recording this presentation, so you can you will be able to watch the presentation with the recording after we are completed. In terms of the schedule, we're going to be Doyle's going to be presenting his slides, and then we're going to, after that, transition to a little bit of a Q&A. So at any point during the presentation, if you have a question you would like Doyle to respond to, please enter that in the Q&A field. Within the WebEx platform that you are all in, you should be able to find a chat and a Q&A. I want to make sure we distinguish those two. The chat is exactly that. It's a chat for the presenters and the attendees. We're happy to look at that. But if you want to get a question in queue, I would make sure you are finding that Q&A module of the WebEx platform. You might have to click on some ellipses on the bottom right to kind of show where that Q&A section is. But if you find Q&A, enter your question there. If all else fails, you need to enter it into a chat. That's perfectly fine. We'll be happy to relay them in the Q&A portion as well. And I think that covers most of the logistics for the webinar. So I don't want to take up too much more time here. Doyle, I'm going to go ahead and hand the microphone over to you, so to speak, and make sure you're able to bring up some slides to walk through. Right. And if you can go ahead and do an introduction for yourself as well, that would be great.
First things first, Brian, can you hear me and can you see the slides?
Yes and yes, good to go.
All right. So hi everybody, my name is Doyle Moats. I'm the NDE Division Director at Texas Research Institute, Austin, out of Austin, Texas. We're a small business focusing on materials science, research and development out here doing work for DoD, Navy, and commercial customers. Today, we're going to be talking about space propulsion and space propulsion primarily from a materials-based perspective. So rather than just going over the different types of space propulsion systems, and there are a lot, kind of, moving it towards a material science bent. What are the materials needs to be able to continue the different types of propulsion systems that we have now that we're already using? And then what do we need to be able to evolve things in the future and achieve goals as we see them in the near term, midterm, and kind of far off perspective. So there we go. It is working. So the overarching themes of this, kind of like I said, are one is organizing space propulsion materials research and how best to accomplish this. There are a lot of different types of engine schemes out there, and how to be able to organize that and present it to everyone in a manner that we can be able to talk about it without just kind of getting bogged down in the vast amount of information. Other things we're going to touch on in this, additive manufacturing. It's already changing things. It's going to keep changing things. Where can we leverage this to be able to optimize things and be able to have the greatest effect on the spacecraft? Miniaturization. So a lot of that is addressing such items as CubeSats, microsats, nanosats of various types that we are going to be deploying in the next few years. And then if I can't make something physically smaller, can I make it lighter? That way I can launch more of them or use a smaller vehicle. And quite often, interesting results come from thinking outside of the box. And so we'll talk about, some of the other types of propulsion that aren't necessarily always mentioned in with other types of propulsion, primarily reaction engines. So breaking out the types of propulsion, there are a lot of different types of space propulsion out there. And let me just start out by saying, if one that you have near and dear to your heart that I don't mention here, I apologize. We've done our best to try and organize them kind of at a TRL level. That way we can provide a cutoff in there that's not arbitrary, but kind of provides something that allows us to be able to say we think this has a decent chance of being used in the not too distant future. And so you can kind of, span the different, sides of that. Solid fuel rocket motors, those are a common item these days when we're trying to launch to space. So TRL-9, flight proven through successful mission operations, versus something like a Bussard ramjet, where the technology concept in our application is, just now being formulated. So TRL-2. So for this presentation, we're putting a cutoff at TRL-6. That way we can have something nice and organized and be able to discuss. So breaking up the different types of propulsion. So we have a very nice diagram here provided by NASA for rocket propulsion. So that encompasses electric propulsion, chemical propulsion, nuclear thermal propulsion. But then there's also another one we've kind of added to this, which is non-traditional propulsion schemes. Non-traditional propulsion, kind of along the lines of what else can I do that's not necessarily a reaction engine of some kind? So things that have been proposed for that and demonstrated over the years include solar sails now, space tethers, and then EM guns, be they a rail gun or be they a coil gun. So starting out with chemical propulsion. So there's a number of different types, and we'll kind of describe these as we go through just for everyone, because to set the stage to be able to discuss material needs, we kind of have to understand what it is that these things are first and foremost. So different types here: solid propellant rockets, hybrid propellant rockets, bipropellant rockets, tripropellant rockets, liquid propellant rockets, air-liquid engines, although those are less common, monopropellant rockets, which are quite common, and then non-reactive propellant engines. Those are commonly referred to also as cold gas thrusters. And all of these are examples of reaction engines. So you have a mass, you react it, and you expel it out of a nozzle, and you get a change in momentum to be able to achieve a change in velocity. Electric propulsion is another one of the topics. So you can kind of break these up into a number of different areas. One of them is electrothermal propulsion, and this kind of crosses an interesting area between chemical propulsion and electric propulsion. You're using a chemical propulsion, you're adding some electrical energy to it, be it warming it or running an arc through it to be able to significantly increase the temperature of the propellant to be able to get more energy out of it. But then kind of more purely geared towards electric propulsion or gridded electrostatic ion thrusters, Hall effect thrusters, field emission electric propulsion, and magnetoplasma dynamic thrusters and pulse plasma thrusters. So nuclear thermal propulsion, the focus for this is solely on nuclear thermal rocketry operating in space. And then propellantless propulsion technologies, as we kind of alluded to previously, mass drivers, so railguns and or coil guns, both of which have been demonstrated on Earth, but neither of which, to my knowledge, have been demonstrated in space. Space tethers, so there's a number of different types of those, electrodynamic momentum exchange, and then you can use them in formation or as an universal orbital support system. And then solar sails, which are being demonstrated as of recent, and have a lot of ideas for technologies on those. So, starting out, chemical propulsion. So, chemical propulsion is a very mature technology. It works very well for launch within an atmosphere or space. We do note that because not all of them do. The fuel gets used up relatively quickly compared to something like electropropulsion, where you have a fuel and your acceleration time is measured in months versus minutes. And there's also a lot of mass required for this in terms of subsystems like tankage, pumps, and then just the fuel and or oxidizer that has to come along for the ride. So the earliest forms of this date back to the 13th century. And there's a lot of different types of solid propellant propulsion out there. Black powder, sugar-based propellants, double-based propellants, so that's two monopropellants. Composite propellants, so a powdered oxidizer, a powdered fuel, all mixed up into a viscoelastic matrix. High energy composite, composite modified double base, minimum signature, smokeless propellant, and electric solid propellant. There's a lot of different ones out there, and then there's a lot of materials concerns to address with all of these. So just some of them, starting to talk about those, are different propellants are used for each one of these different types of categories. And there's a lot of different ones out there. In addition to that, advanced manufacturing of the propellant. For solid propellants, you take the propellant that you have and you cast it to be able to achieve a certain shape. So you kind of see that in the top right plot here for a star shape in the middle. Different types of shapes are going to produce different thrust curves. So you're going to essentially light it off and it's going to burn and provide thrust in a different way. This one is meant to be able to provide a more or less constant thrust over a non-dimensional period of time. Different ones are going to provide more thrust at the beginning and kind of tail off. Other ones are going to provide more thrust at the end and kind of tail off. One thing that some people are starting to do for this is being able to address part of these thrust curves via additive manufacturing. So you can go through and almost like icing a cake, you can create different kinds of shapes within your propellant rather than just casting it. And so you move from kind of a two-dimensional casting almost to a three-dimensional casting. In addition to all this, quality control is a big thing. Solid propellant rockets are designed to be cast, sit for as long as you need, and then operate reliably. Sit for as long as you need isn't necessarily a good thing. You want to be able to make sure that whatever it is that you've cast still works X amount of time later, be it days, months, or years. And so different organizations have sponsored work to be able to do different kinds of non-destructive or minimally destructive testing to be able to confirm that this rocket that I've built, I expect the propellant to operate the way that it was designed X amount of time later. And then thermal protection is another big deal for solid propellant rockets. So thermal protection can either be protecting the interior of the casing after the material has lighted off, so some type of ablative materials on the inside, or protection for the nozzle itself. And so we'll talk a little bit about nozzles in a little while, which include refractory materials, because those are the ones that are most likely to be able to stand up to the high temperatures of the rocket exhaust. The next one to kind of look at is monopropellants. If I say monopropellant, the most common one is going to be hydrazine. Hydrazine is mature. It's been used for a number of years, but there are a number of issues with it. Most commonly being toxicity. The material is not good for humans, and its incompatibility with a large number of different materials. It's very corrosive. So as a result of that, a lot of material science in this area has been addressed towards green, quote, green monopropellants. So one of the big ones here is energetic ionic liquids. And you may ask yourself, what is an ionic liquid? It's a molten salt, and a salt is just characterized as a material that has a set of ionic bonds on it. In addition to that, nitrous oxides have been used, hydrogen peroxide. We do note that some of these also have their own materials compatibility issues. A shameless plug right here is this webinar is kind of being produced as a companion piece to a state-of-the-art report that's being released by DSIAC soon. There is a lot more material on green monopropellants in this state-of-the-art report, and I'm sure, Brian, you'll agree with me here. We highly recommend that you go download that, read it. It is an extensive discussion of all the different materials and material science issues for all the technologies we are talking about today. In addition to this, the next piece is catalysts. So a monopropellant doesn't require an oxidizer to burn. It's run over a catalyst, at which point an exothermic decomposition process takes place. So what do you need in a catalyst? Well, if I have, my wishes, I want something that operates at room temperature that is really, really cheap. Unfortunately, that is not the case. Present day catalysts need heat to be able to operate, and they're typically very, very expensive. One of the most common catalysts is iridium. Iridium is very rarely found on the Earth. The majority of it is inside the KT boundary, for those of us who remember the dinosaurs and the asteroid that brought the majority of the iridium to Earth 65 million years ago. And so a lot of the research here has been dedicated towards, can I find a room temperature catalyst? Is it then cost effective and is there enough of a supply then to be able to actually use it? So other catalysts that you talk about here are going to be platinum and palladium potentially. So those again suffer from cost and supply issues, but not to the extent that iridium does. And then, does this catalyst that I've developed have the ability to retain the necessary properties at the high temperatures once the monopropellant has ignited and it does get heated up in the first place? Excuse me. So in addition to that, some of the other things that they're looking at for this is being able to 3D print catalysts in very specific shapes to be able to use more surface area, to be able to drive down some of the temperatures necessary to start the reactions at. So there's a number of different areas that this is that the different material science perspectives kind of go into for all of this. Moving on. So cold gas thrusters. So cold gas thrusters are highly desired by the CubeSat manufacturers and those who use them because it's a non-reactive. It's a low-risk technology, and there's little chance of it interfering with anything on the CubeSat side of things. The primary areas for materials research here focus on propellants. There's lots of different propellant types. There's lots of different esoteric propellant types also being developed for this. And then associated support systems. How can we optimize the existing mature topology to be able to make it lighter weight or make it more efficient? Again, and you'll hear it a lot here, and I apologize that it keeps on coming up over and over again. Additive manufacturing is kind of being used here to be able to develop new ways to be able to shrink down the footprint of existing systems, or to be able to optimize nozzle diameters and nozzle characteristics or different pieces of the system to be able to eke out that last little bit of efficiency out of the system. New combinations of materials and manufacturing methods are being tried. New propellant methods are being tried. Normally, if you think, a cold gas thruster, you might just think, okay, nitrogen thruster, but some are using iodine as fuels now. There's a lot of different options out there. One was using naphthalene as a fuel. Chemical propellant, liquid propellants. Oxidizers and fuels are needed for these guys. So we're moving away from monopropellants. We have now a fuel, an oxidizer, and in the case of a tripropellant, a fuel, an oxidizer, and metal or something like that mixed in to make things interesting. This also includes hypergolic propellants such as hydrazine hydrate or high concentration peroxides. Excuse me. And then the materials issues for this and the materials issues for all of the kind of chemical propulsion as we kind of, look at those, motor casings and our pressure vessels. So you're going to light off an explosive and you want it all to go one way and the rest of the system not to explode itself. That means that you have to be able to develop materials and develop quality control methods to be able to do that. So the most common ones for these are going to be aluminum and probably lighter alloy aluminums like aluminum lithiums. In some cases, steels are being used for this. And then there's pushes for carbon fiber reinforced polymer composites to be used as well. In addition, nozzling is a big deal. And part of the reason that nozzling is a big deal is because things like aluminum and steel and CFRP no longer work. You have to transition now towards refractory materials or some form of refractory material that has a high temperature melting point and retains its structural properties as close as possible to that high temperature melting point as humanly possible. And so often for that, the solution is refractories. And by refractories, we mean materials like tungsten and molybdenum. One thing that comes along with those is a very high density, and so very high weight. Some work is being done in producing things like tungsten foams that are then covered with a sheet of tungsten on them that allows you to be able to retain the geometry of a nozzle that you want, but be able to overcome some of the mass issues that come along for the ride with that. Another area is sealing. For those of us who remember the first STS launch recently, one of the problems that was had there was with hydrogen leaking. Hydrogen has to be cooled to very, very low temperatures and does have a propensity to leak. And so as a result of that, any engine that's going to be using hydrogen, so that would be a nuclear fueled rocket for an example, needs to have very good sealing on it to be able to avoid hydrogen leaks. And for all of this, quality control is a very big deal. So that can take any number of forms for any number of these things. There's no one size fits all solution to any of this. So for quality control, you're often talking about non-destructive evaluation, which could be ultrasonic inspections, electromagnetic inspections, eddy current inspections, X-ray CT inspections, to be able to look for any sort of defects in any of these things that are going to cause potential mission failure. The reason so much time is kind of spent on quality control for this is these missions are typically very, very expensive. And so if any one thing can cause mission failure, even if it's just, a defect in the nozzle or something like that, one thing does it and you can't get around that. Excuse me. And so now we kind of move towards electric propulsion. So electric propulsion, very mature to reasonably mature. By and large, it's suitable for in-space use only. So that means exo-atmospheric with the possible exception of arc jets and resistor jets. The engines are very efficient, but they're very low acceleration. They can be run for very long periods of time. And they can also achieve very precise levels of force. One of the notable successes for this was the recent Dawn mission that was operating off of an ion engine that went into orbit around Vesta, broke orbit of Vesta, and then moved on to Ceres. So the first one to focus on here is electrothermal propulsion. Excuse me again. So this kind of combines propellants and electricity. You get an arc jet and a resistor jet. An arc jet just moves energy through some kind of a filament. You get I squared R heating, and you're able to get a little bit more work out of the system. That was a resistor jet. An arc jet, now you're drawing an arc between a cathode and an anode. You're dumping a lot more energy into it, and you're also having to be able to accommodate that by having significantly arc-resistant materials in the entirety of that reaction chamber. Now, the cathode, the anode, and the area that you're having to insulate and move possibly a plasma through. And so your material concerns for this are, there's a million different ways you can leverage additive manufacturing to be able to help with these problems. Cathode materials and anode materials do become an issue. You do start to see erosion on these. Miniaturizing these things is something that a lot of people are interested in. And then different types of propellant gas for this. Different propellant gas are going to be able to get you different options in terms of, how quickly can I move gas out of this thing and be able to get a reaction out of it. Next one is gridded electrostatic ion thrusters. In this one, propellant is ionized in a discharge chamber via an applied voltage and ejected from the spacecraft to be able to create thrust. One of the pieces of this that is interesting is to achieve a neutral net charge, you have to have a neutralizer placed near the engine to emit a beam of ions out such that you don't accidentally develop a net charge on the spacecraft. So a lot of these next engines kind of follow a similar type of bent, but they're all different in their own ways. Hall effect thrusters, they're kind of a similar version of an ion engine, but their architecture is a little smaller. Excuse me. For these, xenon is the most common propellant. These have been flying in space for a long time. They're supposedly in use on China's Tiangong space station, and they're planned for use on NASA's Lunar Gateway. And so using one of these on NASA Lunar Gateway, one of the things that you immediately think of for this is, oh, that's a pretty large structure. We're going to need to be able to develop these into a larger size and scale up. And that's something that we'll talk about from a materials perspective in a minute here. The other piece of this is that they have a shorter lifetime than grid and ion engines. This is a FEEP thruster, so a field emission electropropulsion. It is a very low thrust, but is very precise, used primarily for attitude control. This is operated via an E-field applied between two ends of a tube or a plate, and then an accelerator to be able to create a Taylor cone, which is this jet that you see here in the upper right, or this little thin tendril that you see on the bottom right. At a high enough voltage, positive ions are emitted. So ideally, a fuel for this that you need is going to be a room temperature metal that can flow through narrow parallel plates and tubes, have a low ionization potential, and a high atomic number. So these are primarily used on CubeSats, microsats to be able to have a very precise thrust, to be able to operate it, and simply on a larger spacecraft, they're just not going to do much to be able to move it one way or the other. Magnetoplasma dynamic thrusters, also known as an MPD, arc jet, or a Lorentz force thruster, they operate somewhat similar to an arc welder. Numerous propellants have been examined for this type of thruster, one of them being lithium. Materials issues with this are much like some of the others. Since you're drawing an arc, you have a cathode and an anode again, and now you're back to making sure that you have erosion resistant materials to be able to accommodate the fact that you're drawing an arc. Pulse plasma thrusters. So this is somewhat like a capillary discharge, if anyone is familiar with that. This uses an arc to be able to subliminate or ablate a solid propellant and be able to eject that out. So it's good in the sense that you now can take a large amount of fuel and shrink it down and be able to accommodate some volume. You can tailor your thrust. There's a wide range of available fuels for this one. The one you're looking at here is a Teflon block in the diagram. And once again, the same kind of theme that you see everywhere here. Anode and cathode erosion is a problem that you have to overcome and work around. And so, from a pure materials perspective here, what are the universal issues that we're looking at? So, one, electronics protection. So you want your electronics to be, since the engines are built around that, shielded, rugged, and radiation tough. Alternative fuels is a big thing. So when I talk about all these, one of the most popular types of fuels for this is xenon. Like everything that we're talking about here, supply chain kind of comes back to you and cost kind of comes back to you. Xenon is used because it's been the easiest to be able to build systems around, but at the same time, xenon is not the most widely available noble gas there is out there. People have talked about what can we transition to something that we have more of? Argon, krypton. Some have talked about using iodine. Those are being developed, but then you have to start to think about what happens when I use these alternative fuels. Do I get a lower efficiency, or does something even stranger happen? One example of this is iodine has been found to resublimate after it's been used in one of these engines on the outside, in which case that is a particularly aggravating scenario. So cost, availability, and how good does it work? Another item is, where can I leverage AM in each of these different types of technologies? and what materials can I use it with, and then what research needs to go into expanding the number of materials I can use AM with to be able to optimize or open up new possibilities. Miniaturization is another area that's being addressed here. So can I take these devices and shrink them down to be able to use them on ever smaller spacecraft? Low work function insert materials is one. If you're like me and you had to Google what a work function is, so it's the minimum amount of thermodynamic work to remove an electron from a solid to a point in a vacuum outside of that solid. So these examples of this being developed right now are combinations of barium oxide and tungsten. In addition, lithanium hexaboride is being developed for this. As I kind of also alluded to throughout this, anode-cathode material combinations that do not erode. Erosion is a big problem whenever you are drawing an arc between two things. Avoiding sputtering on the outside of engines as a result of the ion plume. Another one is electromagnetic compatibility. So this needs to be done in the early design stages when you're designing a spacecraft, but you want a material selection between all of the different components that don't cause unintentional generation, propagation, or reception of EM energy that may result in EMI or physical damage to any of your components. And then another one is testing, which you wouldn't think would be a materials consideration, but it kind of is. The particle density in space is on the order of 1 atom per centimeter cubed. And there's not many places on Earth where we can achieve this. We can get close, but getting close may not necessarily give us a true idea of how these devices behave inside a true vacuum and a hard vacuum. And then in addition to this, the future for where a lot of this is going to be building up the materials library and capability to be able to meet the upcoming demand for all of the different types of smaller satellites out there. So if we're talking about things like SpaceX's Starlink, where you have constellations of smaller satellites operating to be able to achieve a particular function, and then scaling these up in terms of size. If now we kind of go the different direction and we're looking at NASA's Lunar Gateway, we need very large versions of this to be able to effectively move the gateway from one orbit to another. Now we'll kind of turn to looking at nuclear thermal propulsion. So with this, where we have a hydrogen propellant being stored, we take a complicated situation, make it a little bit more complicated. You start out with having a lot of cryogenically stored hydrogen and a lot of radioactive material. You launch it, you heat up the reactor and operate it. Hydrogen flows through the reactor, heats up, expands through the nozzle, producing thrust. It sounds simple, there's a lot of individual systems here. One of the major barriers to demonstrating high-performance nuclear propulsion is developing a fuel that can survive the extreme operating conditions that are required during spaceflight. Fuel operating characteristics that need to be satisfied during reactor operations are going to include minimizing high-temperature hydrogen corrosion, minimizing brittle fracture behavior at low temperatures, because again in space you're going to be cycling between very, very hot and very, very cold. Minimizing fuel creep and vaporization at high temperatures, minimizing radiation damage that will impair fuel performance, managing high transient thermal and mechanical stresses on the fuel during startup, rapid heat transfer from the fuel to the propellant, matching thermal expansion coefficients for different materials, low fuel and reactor system masses so that you minimize launch costs, because this thing is going to be heavy, limiting fuel dissociation and constituent migration during reactor operation, and limiting fuel cracking and coatings to minimize hydrogen ingress into the fuel during reactor operations. In addition to all that, you need to be able to consider control rod and drum assembly, reflectors, and nozzling. There's a lot that has to go on with this, which is part of the reason why this particular type of engine has not been tested outside of the atmosphere yet. Work is being done, but at the same time, there's not plans to be able to physically build one of these for testing at the moment. And so finally, we kind of transition to propellantless propulsion. So this was kind of developed as a catch-all for the other propulsion methods that reach a TRL cutoff that we're talking about, but don't fall neatly into any one of these other categories. We think about this as no stored propellant being needed, stored propellant being the traditional sense for this. So the first one we look at is mass drivers. Mass drivers are a mature technology to some extent on Earth, not in a vacuum. They come in two flavors for what we're talking about here, so that we're not talking about a traditional gun. We are talking about a rail gun or a coil gun. These type of devices are capable of very large accelerations in a short length, but they require very large electrical currents to come along for the ride, and very, very fast switching if you're talking about a coil gun. In addition, since you're talking about very, very large electrical currents, you're now talking about the potential for large arcs. And thermal management also becomes a problem with this. Excuse me. In addition, moving on to solar sails. These are being recently tested in space now. The most common configuration for these is going to be an aluminized mylar. So the goal here is, can I get this large square footage item up into space in as light a way as humanly possible? The reason we talk about these is these offer very high potential velocities, but there are a number of issues that come along with the ride, as with everything. Mechanical is the first one. So you want to be able to create an optimum structure for the sails, have them supported, and an optimum substructure for everything. So the minimum amount of mass that you can do this with, because you're already going to have a very, very large area that you are going to have to support over, but you don't want to eat away any parasitic mass, have to have any parasitic mass in the system or anything like that. Thermal management. There is talk about being able to operate with purely dielectric sails. That way you can do a better job of rejecting heat from one side to the other. People are talking about creating an optimum structure that has an emissivity of 1 for the part of the EM spectrum that the sail is being irradiated by, and a reflectivity of 1 for everything else. So you would tailor your material, possibly a metamaterial, to be able to have a emissivity of 1 over the majority of the sun spectrum and cut off right after that. Integration of enabling technologies, so that can be structural support, that can be a number of different things. And most importantly, which is why it's bolded and capitalized, we need to make them much, much, much bigger. If we're talking about being able to use these on a spacecraft that's going to be larger than a CubeSat, we need to have these very large, and we need to have the production capabilities to be able to make these very large. Another propellantless propulsion technology is space tethers. A recent example of this was in 2022 when NRL demonstrated a CubeSat space tether in space. Tethers can provide power and or propulsion. Different tethers have different purposes. The one NRL tested was a metal-coated 9-strand wire. In addition to this, it's a Kevlar Aircon tether. So now we're also moving from, for those of us who are more comfortable with metals and composites, into the textile ring. Primarily, composite is used to be able to optimize conductivity if you have a metallic coating on it, and strength. Electrodynamic tethers are going to need some kind of a conductor on them. Momentum transfer tethers are more like a rope and release and are going to need to primarily focus on just strength. But strength is something that's very, very important, and there's a number of different ways that people are looking at decreasing the weight and making them stronger. Crystalline plastics, monocrystalline whiskers. The near term may end up focusing on lower risk materials than some of these that can be produced in small quantities so as to better demonstrate spacecraft performance. So we've gone through all of this, and now who's paying for all this? Who's funding it? What do they need? What do they want? Why do they want it? So in the United States, the number of different people or organizations are looking at these. NASA is developing technologies related to exploration and their ultimate goal. NSF is primarily concerned with basic low TRL technologies, so a lot of high-risk items are going to get funded through the National Science Foundation. DoD is another big funder of these. They do applied and basic technologies and cover the Navy, the Air Force, the Space Force, MDA, and DARPA. And then a number of private industry organizations have spun up in recent years that are involved in moving humans to various forms of orbit, be it SpaceX, Blue Origin, or Firefly. Foreign agencies are looking at funding in different areas are the European Space Agency, the China National Space Agency, the Russian Federation Space Agency, and the Japanese Aerospace Agency to kind of provide a limited selection. Taken from their publicly available websites, their focus for propulsion is ESA is focused on storable, hybrid, and solid and methane-based propulsion. And so as a result of that, materials science is going to be dedicated to those. The China National Space Agency has a publicly available website, but the material is limited, as one might imagine. They state they're focusing on the development of, quote, innovative propulsion technologies, propulsion for space debris cleanup, and for in-service orbiting. The Russian Federation Space Agency, their research focuses for propulsion on the Angara launch system and enhancements to Soyuz. They are suffering from the effects of the Ukraine war, though, we note. And the Japanese Aerospace Agency has taken on a lot of research with a focus on electropropulsion in one way or another. Wrapping up things, the United States and near-peer nations are continuing to push more technology into space and in the Earth-Moon system. Advances in technology, such as additive manufacturing, are driving lower mass and miniaturizing propulsion systems and coming along to deal with miniaturized spacecraft now. Alternative fuels are going to increase the availability of propulsion systems to a wider range of missions. So private missions, primarily such as moving tourists, exploratory missions can be robotic, and then military missions to address satellites to be able to identify launches from near-peer nations. CubeSat and micro/nanosat formation flying is going to be driving the production scale miniaturized propulsion systems. We need to be ready both to be able to create large scale versions of these from a materials perspective and be able to create large limited versions of these from a materials perspective. And with that, I think I've come to the end of my little speech. And thank you very much for listening to me for this long.
Thanks, Doyle. No, that was great. Very good presentation. I'm glad that you gave the shameless plug for the upcoming state-of-the-art report. I'll just reiterate what was mentioned there and also in the chat, which is that we're hoping to have that published and released sometime in September or thereabout. So everyone can be on the lookout for that. You should, if you are a DSIAC member and you receive some of our emails, digests in particular, then you will be able to get an email notification when that report is released. And at the very least, you can check out our state-of-the-art report section on the website for when that report is published on there. So yes, much more to come related to this in that state-of-the-art report. So I should have, while I was talking there, I should have pointed everyone to the Q&A section. We're going to transition now to a couple questions for Doyle to respond to. Again, in the WebEx platform, there should be a Q&A section. You might have to click a couple ellipses and select Q&A, but it'll allow you to enter a question that then I can pose to Doyle and he can respond to it. So we have a couple already in queue. I just wanted to remind everyone about that, and then I'll fire them off to Doyle and we can just take them in order. So Doyle, if you're ready, let me go ahead. Looks like one of them.
I'll do my best.
Yep, I'm just making sure we got the right ones in queue here. All right, first one is asking if field emission electric propulsion, if that exhausts, does field emission electric propulsion exhaust the liquid metal?
It exhausts ions from the liquid metal, so I believe the answer is yes. I don't know how long your fuel supply will last, though. So.
Okay. All right. All right. Next question says, to my knowledge, AM has notoriety in the past for producing less dense products compared to more traditional sintered or cast fuels. Does this have a significant impact on the use for solid rocket fuel systems with regard to overall efficiency?
No, it's probably going to have a number of different effects. So that AM producing less dints in terms of pores and voids is something that you see both in metallic objects that you make from AM processes that would normally undergo an annealing, a hip, and a sintering process. But yes, so that's going to affect a number of different things. The first is that it's going, if you create large voids or you have large propellant grains, those aren't necessarily going to burn uniformly, and you may end up with small areas that don't combust, surrounded by areas that do combust, which can create local pressure differentials. So there's a number of different things that need to be addressed before that, I suppose, before that technology is completely adopted and ready for prime time. It
Yep.
is an area of research that offers a number of exciting possibilities, but much like with everything, there are a number of things that you have to look at. And especially when you're adopting a new technology in one particular area, you probably want to focus a lot more on developing quality control mechanisms for this so that you can be sure that these different types of technologies do perform the way that you expect and you don't have any nasty surprises.
Yep. Very good. All right, thanks. Looks like the next question we have in here says, what types of space propulsion is the Navy most interested in? If you
Um,
know.
I do not speak for the Navy. Let me just state that. I do know that a lot of what the Navy a lot of what the Navy does is related to missile launch. And so missile launches are primarily solid propulsion, especially for the SM-6 and the SM-2, which are launched out of the Mark 41 on a lot of our guided missile destroyers. And so that would point towards the Navy being very interested in solid propulsion rocketry. There has been a number of Navy requests for proposals over the years that address quality control for Navy rocketry, specifically related to, I've had this piece of ammunition stored for a long time. Do I still believe that the propellant is going to light off as it's designed to and behave in a reliable way? But like I said, I do not speak for the Navy.
Of course. All right, and let me just quickly interject, if I could, for DSIAC, another shameless plug. If you all aren't aware, we have a free technical inquiry research service. So any of these questions would be perfect for submitting to us as a technical inquiry, and our analysts, our researchers, Doyle being one of the subject matter experts that we go to, will help us get a kind of fuller answer and response to some of these questions. So feel free to take advantage of that. It's a again, a free service for government and government contractors. So all right, next question that came in asks if is magnetic force itself, is that a method used for any techniques
Yes.
you know of?
Coil guns and rail guns are going to utilize magnetic force. So with those, you use a very high current pass through, in the case of a rail gun, a solid armature that then creates the Lorentz force necessary to launch the projectile. For the coil gun, it kind of sits in the middle of a set of coils. You don't have the same problems associated with a rail gun that you do with a coil gun. In a rail gun, you now have sliding contacts, one stationary, one going kilometers per second, which provide for some very unique failure mechanisms called hypervelocity gouging that, if anyone here is familiar with rocket sled tests from the 1950s, those are where we first saw those. And then especially the use of an armature means that you have molten aluminum coming along for the ride. A coil gun gets away from all of that, but a coil gun requires very, very, very fast switching devices to be used for that, so that you have a number of coils that are lined up and you essentially use the difference in the magnetic field as you switch one coil on, one coil off, next one on, to be able to slowly and then faster and faster move a projectile down a quote gun barrel. But as a result of all of these very fast switches, you now have very high inductive voltages that are introduced in the switches, and you have very high currents running through the switches to be able to accommodate all of this. And so from a materials perspective, you're now talking about having to make sure that the switching for this, which in many cases previously is used diode stacks or ignitrons, can be able to accommodate what's necessary to be able to accelerate your mass to whatever velocity you want.
Okay, thanks. Sounds like a topic near and dear to your heart.
Yes.
All right. Another question we had asked if you have any thoughts about rotating detonation engines in the DoD, like any particular material perspective on rotating detonation engines.
I do not. I did not prepare anything for that. I would advise that individual to please submit that through the technical inquiry. So if they're interested in more research on that, some of the DSIAC guys can take a crack at that and get them some good information here.
Yep, thanks. All right, and it looks like maybe the last one we'll get to is just if you have any comments on the advantage, I'll say from maybe a materials perspective, but advantage of hypersonic vehicles compared to hypersonic missiles, or maybe differences from a material perspective when you're talking hypersonic vehicles versus missiles.
I think that there's a number of different ways that could get interpreted. If a hypersonic vehicle is meant to be a reusable vehicle versus a missile, we tend to think of a missile as a one-time only, which means it's going to have a certain type of thermal protection system. And if it is an exo-atmospheric versus an atmospheric, such that it has an air-breathing engine, that's going to have an entirely different set of materials that are required for that versus an exo-atmospheric one, or one that operates in both, than one that is operating as a hypersonic vehicle that's going to be landed and reused again, which may mean that there may be passengers or cargo or something like that, which if you're talking about that, now you're talking about a lot more regulations that have to come along for the ride in terms of quality control on the manufacturing side for the materials in question, and then constant inspections of the quality of these materials through their lifetime in a similar fashion that you would for a civilian or commercial or military aircraft.
Very good. All right. Well, thanks. Let's see. I'm just gonna scan over. Let's just get one last one thrown in. And I'll just kind of read it here for you. It says hydrogen is typically the propellant of choice for NTP systems. With the recent DoD and NASA collaboration for Draco, would the change in scope for a lunar mission allow for use of a less efficient propellant such as helium that could eliminate hydrogen attack on the fuel?
I do not know. I am not familiar with that to be able to provide an intelligent answer. I do know that for helium, hydrogen is a lot more common to find in helium. You can run electrolysis on water and be able to produce hydrogen to your heart's content. There is a worldwide helium shortage right now, and so I would just say that one of the issues that will come along for the ride with that, regardless of whatever else there is simply getting your hands on helium.
Right. Okay. No, thanks, Doyle. Well, I want to honor our time, and we're getting here close to 1 o'clock Eastern time. So thank you so much, Doyle, for the presentation. Thanks for everybody for joining. As already mentioned, we've been recording this, so we'll get that recording available and send a follow-up note to everybody about that. And again, keep a lookout for the state-of-the-art report. And if you have any particular questions in the meantime, you can submit it to DSIAC through our technical inquiry service, and we'd be happy to help you. So everyone have a great day. And again, thank you, Doyle, for your time.
You guys take care. Stay safe.